everyone, I am Ana Rose Tila Chica,
And I am Lumnik P. Bunghaloy.
and we're going to discuss about the Poisson distribution.
Poisson distribution is a type of discrete probability distribution. It is used to know the number of occurrences in an interval.
Its density function is f sub x of x is equal to lambda to the power of x times e to the power of negative lambda all over x factorial. The mean of the Poisson distribution is equal to lambda, and the variance of x is equal to lambda.
Example, if a typist makes errors at random at a mean rate of 2 per page, find the probability of making A, making no errors, B, making more than 3 errors on a page. Note that 2 is the mean rate of the error, meaning lambda is equal to 2. A, making no errors. So if lambda is equal to 2, then first let us let x be the random variable. Then let us use the formula. Let us get the probability of making no errors. So x is equal to 0, and let us use the formula of the density function. E to the power of negative lambda times lambda to the power of x all over x factorial. Then let us substitute the values. E to the power of negative 2 times 2 to the power of x 0 all over 0 factorial. If you input this in the calculator, the answer will be 0.13533. So the probability of making no errors is 0.13533. Now, let us get the probability of getting more than 3 errors. So, it should be the value should be subtracted to 1 because 1 is the overall probability, diba? So, 1 minus the probability of x is equal to 0 plus probability of x equal to 1 plus the probability of x is equal to 2 plus the probability of x is equal to 3. Now, let us use the formula of the density function and input these values where lambda is equal to 2. Then, e to the power of negative lambda times lambda to the power of 0 over 0 factorial plus e to the negative 2 times 2 to the 1 over 1 factorial plus e to the negative 2, 2 to the 2 over 2 factorial plus e to the negative 2 times 2 to the 3 over 3 factorial. If you input that in the calculator, the answer will be 0.85712 and so on. And the answer will be 0.14287 and so on. So it is approximately 0.4143. So the probability of getting more than 3 errors is 0.143.
First, we need to get the moment generating function. By chapter 2, definition 19, we have m of sub x of t is equal to the expected value of e to the tx is equal to the summation of e to the tx f sub x of x. So now, we have the summation of e to the power of tx times e to the negative lambda times lambda to the power of x over x factorial, where x started from 0 to infinity. Next thing to do is we need to factor out the constant, which is e to the negative lambda times the summation of e to the tx times lambda to the power of x over x factorial, where x started from 0 to infinity. Next, we have, since the exponent have common, so we need to factor out. So we have e to the negative lambda times summation of e 1 to the power of t times lambda 1tt to the power of x. So we have this one. Note our x started from 0 to infinity. Note that summation of e to the power of t times lambda quantity to the power of x over x factorial is a polynomial function which is an estimation of Maclaurin to the equation e to the power of y. So we let y is equal to e to the power of t times lambda. So the summation of e to the ty, e to the t lambda over x factorial, where x started from 0 to infinity, is equal to e to the power of t times lambda. So now we have our moment generating function is equal to e to the negative lambda times e to the power of t times lambda, or simply as e to the power of t times lambda minus lambda. So now we have our moment generating function.
This time, we need to prove that the expected value of x is equal to lambda. This time, we need to prove that the expected value is equal to lambda. But before that, we have to get first the first derivative of the moment generating function. So we have m sub x of t is equal to e to the power of e to the t times lambda minus lambda. So in this case, in order to get the first derivative, we can use the u to the u prime. So now we have our u is equal to this one is whole. So e raised to the power of e to the t times lambda minus lambda. Then our u prime is the derivative of the exponent. So we need to get the derivative of this one. So we have this u to the u prime. So this one we are going to get the derivative. So u prime is equal to the derivative of e to the power of t times lambda minus lambda with respect to t. So in this case, since this one we have two terms, so we need to get the derivative of each term. So we have the derivative of e to the t lambda plus the derivative of negative lambda with respect to t. So next thing to do is, since lambda is constant, so we need to factor out. So we have lambda times the derivative of e to the t with respect to t plus, since negative lambda is constant, so the derivative of the constant is equal to 0. So we have 0. Then lambda times the derivative of e to the t is equal to e to the t plus 0. Then we have lambda times e to the t. So our u prime is equal to lambda times e to the t. Thus, our first derivative of moment generating function is equal to e to the t, e to the power of e to the t times lambda minus lambda times lambda e to the t, which also equal to lambda times e raised to the power of t times a raised to the power of e to the t times lambda minus lambda. Note that the a to the t and e raised to the power of to the t times lambda minus lambda have the same base. So in this case, we need only to add the exponents. So we have lambda and just copy its base. So we have e raised to the power of e to the t times lambda minus lambda plus t. So now we have our first derivative of moment generating function. So in order to get the expected value, we have the expected value of x is equal to the first derivative of moment generating function where t is equal to 0. So in this case, we need to substitute t to 0. So we have lambda times a raised to the power of e to the 0 times lambda minus lambda plus 0. So next we have lambda a raised to the power of, since e to the 0 is equal to 1. So we have lambda minus lambda. So next we have lambda e to the power of lambda minus lambda is equal to 0. So we have lambda times e to the 0. Since e to the 0 is equal to 1, so we have lambda. Thus, our expected value is equal to lambda. So we have our expected value which is equal to lambda.
This time, I am going to show that the variance of x is equal to lambda.
In getting the variance, we need to get first the second derivative of the moment generating function. Note that we have our first derivative m sub x prime of t is equal to lambda times e raised to the power of e to the t times lambda minus lambda plus t. In this case, we need to get the second derivative of the moment generating function. So to get the second derivative of the moment generating function, we can use the u to the u prime. So we let our u as equal to lambda times t raised to the power of e to the t times lambda minus lambda plus t. So we have our u is equal to lambda times e raised to the power of e to the t times lambda minus lambda plus t. So now we need to get the u prime, which is the derivative of this of the exponent. So we have derivative of e to the t times lambda minus lambda plus t. So note that the function composed of three terms. So we need to get the derivative of each term. So we have d over dt of e to the t times lambda plus the derivative of negative lambda with respect to t plus the derivative of t with respect to t. Next thing to do is we need to get the derivative of each term. So note that lambda is constant with respect to t, so we need to factor out. So we have lambda d over dt of e to the t plus, since lambda is constant, note that the derivative of constant is equal to 0. So we have 0 plus the derivative of t is equal to 1. So now we have lambda, the derivative of e to the t is equal to e to the t plus 1. So thus our second derivative
of moment generating function is equal to u times u to the prime. So we have lambda a raised to the power of e to the t times lambda minus lambda plus t times lambda e to the t plus 1. Uh, Now we have our second derivative of moment generating function. In getting the variance, we need to get first the expected value of x squared. So we have expected value of x squared is equal to the second derivative of moment generating function where t is equal to 0. This time, in order to get the expected value, we need to substitute t to 0. So we need to substitute this one to 0, this one, this one. So we have lambda times e raised to the power of e to the 0 times lambda minus lambda plus 0 times lambda times e raised to the power of 0 plus 1. Remember that a to the 0 is equal to 1. So we have lambda times e to the raised to the power of lambda minus lambda times lambda plus 1. Since e to the 0 is equal to 1, also this one, e to the 0 is equal to 1. That's why we have this function. Then we have, since negative lambda minus lambda is equal to 0, so we have lambda times e to the 0 times lambda plus 1. Again, e to the 0 is equal to 1, so we have lambda times lambda plus 1. Note that the variance is equal to the expected value of x squared minus the expected value of x quantity squared. So we have our expected value of x squared is equal to lambda times lambda plus 1, and our expected value of x is equal to lambda, so we have lambda quantity squared. So this time, we need to multiply this one to this one. So we have lambda squared plus lambda minus lambda squared. So we have lambda squared minus lambda squared is equal to 0, so plus lambda. So therefore, our variance is equal to lambda.